All right, this is Mike. It's Thursday, April 30th, 2020. These are your theory videos for this week. Now, I'm going to take up one question from the handout, Level 2 Power Factor Correction Practice. That's what it was titled. It starts off with some short answer questions, and then it gets into the calculation questions. I'm going to take up probably the most complex question. We're going to do it a couple different ways. So it was question 8 in this handout. A 240 volt, 60 hertz, 5 horsepower motor is operating at an efficiency of 85%. Stop right there. That's one statement of the question. The load is a motor. It's 5 horsepower. It needs 240 volts. The efficiency of the motor is 85%. When we're talking about efficiency, this is different than power factor. Efficiency applies specifically to the equipment we're operating. Power factor is the circuit as a whole. So the efficiency of the motor is 85%. So we have to calculate the efficiency. So the motor requires more power in to get 5 horsepower out. And then the circuit's power factor is 0.7. So there's two let's say deficiencies we have to apply to this circuit to be able to calculate it. So I put 5 horsepower in purple because that's power, and I put the efficiency 85% is also that's going to equate to our total power for the circuit. So with that information, A wants to know, calculate the size of capacitor in VARs used to correct the power factor to 0.9. We first have to establish our VA power in VARs at the current power factor of 0.7 before we can correct it to 0.9. I've already gone ahead and drawn 2 triangles. I've color coded them with the consistent colors we've been using. Green for VA, purple for power, red for watts, and then our angle or power factor is in blue. So you can see I know nothing about the 0.9 power factor other than that the wattage of the equipment we've powered or we're going to power is 4,388 watts. That will not change. Go back to the first triangle, 0.7 power factor. How I calculate my watts was, we first have to know that 1 horsepower equals 746 watts. So I've drawn it over on the far right with our color coding scheme there. Now, this motor has 5 horsepower times 746 watts is 3,730 watts. Now, because the motor has a certain amount of inefficiency because it's an inductive load, so we're going to have some inefficiencies. It's 85% efficient, which is okay. So it's going to require 4,388 watts in to get 3,730 watts out. We can't change that. That's how the motor's been built without tearing the motor apart and adding in some components or reconstructing it. That's the characteristics of this motor. They do not change. So we put P equals 4,388 watts. Done. That's why I can automatically take the wattage from 0.7 power factor and move it over to a 0.9 power factor. Because the power factor, don't forget, is are going to be our line current leaving our breaker, where the load is, it's a fixed variable. We're not adjusting the load, but we can help the circuit's overall efficiency. In this case, it's called power factor. So that's the first step for step A. Step A, I have to calculate my watts. And how I got from the 3,730 is I divided it by the 0.85. I took 85%, I moved it into a decimal. You can see there I didn't use 0.7 to calculate my watts in any way. That'll come next when we calculate our VA, which will be the next segment of this video.